I introduce myself briefly. I'm Cesare Rizzo. I'm at the Genoa University, but I would like also to introduce all of us. There is a quite huge group that formed several years ago, 5 or 6 years ago, around a European project. The European project was focusing about the validation of digital robotic and remote inspection technologies.
Can I just ask all to mute
okay.
the microphones, except you, Professor?
Yeah, okay.
Thank you.
I'll continue.
Yeah.
So it's a quite good group with people here, and Tommaso Gaggero is also today here, but there are others, professors and postdoc and PhD students and so on, that are involved in the team. Basically, the idea today is to provide an overview of what we did since the beginning of that project, and even today with new project ongoing, telling how the evolution of technologies can be exploited, but should be exploited with some care, and we should take care about validation. So we, beside the technologies and the engineering, we learned some important lesson, and we do believe that is interesting for the shipping community to make a rational overview of what means validating the technologies for such inspection, to make them really reliable. And that is the content of the presentation I summarized in this slide. Basically, today, I don't have to tell you that the today are human-based, and they are mainly visual inspection, and the means of access are what the ones that you well know. And I well remember, because I was a surveyor, what means to be on a scaffold, to be on a raft, and to work as a surveyor in the field. But let's step a little bit back. What means an inspection? What is the rational framework for an inspection? Then we should try to summarize what is an inspection by asking ourselves why we do an inspection. So we do an inspection for safety, environment, efficiency, and everything. And then we should ask ourselves who is doing the inspection, when we do the inspection. So at a point in time, but with the age of the ship, which operational condition. So when, in a broad sense, where we do the inspection, where means where we are looking at, or where in the world we are, what we are looking at, which item we are checking, which degradation mode we are looking at, and how we do that. So we are looking at how. We are looking at the survey methods, and we are looking at the scope and extent of the survey. And then we have different technologies. At that time, I mean, 5 or 6 years ago, we started the project, and we tried to involve in the project really 3 or 4 families of technologies. But these families of technologies means not only robot, not only aerial drones, but technology as a whole. I mean, we have a robot, we have a drone, but we have the camera, we have the streaming video, we have the telecommunication, we have the piloting aids, and so on. So we are trying to use technologies, but these technologies are really developing a lot, and they are developing very, very fast, we shall be prepared for any new idea, but we should also take into account that we are using combined technologies. We saw about thickness measurement 6 years ago, were just beginning or maybe not available. Now they are almost available, almost reliable. That means a new era, because we involved a new technology in a combined robot with several other technology. But then at that time, and even nowadays, we are asked, which are the challenges in validating the digital and robotic inspection on board? Why we need to validate? It's clear. We need to validate the technology because we would like to have a reliable inspection result. But to do that on board means that we have a limited availability of ships and crews. It may happen, as we saw, that there are some ships available, but not many ships to make a huge statistic. It's difficult to have a broad range of degradation condition. You can't have all the degradation condition and effects you wish to assess. You need to have trained personnel, and that personnel should be trained for novel techniques because technology is advancing. Of course, the guidelines are not available. If we are here, there are no international agreed IMO document for that. But in any case, we should demonstrate that robotic technologies are available, and we agreed after the first round of the correspondence group that the performance must be demonstrated equivalent. So that is a result that I think we reached a few years ago within the project I mentioned. We said we need to compare with human inspection result, because the human inspection result, that means the current inspection regime, is somehow satisfactory. So at least with this new technology, we need to replicate that standard. To validate then this technologies, any technology, I mean, we need to demonstrate the equivalence. And then we need to compare with the current human inspection result. And to do that, we decided to identify the critical factor to use the new technologies, to identify protocols and evaluation criteria that are standardized, and then to build up a measurement system for such robotic technologies that are a system for measuring the degradation of the ship hull, the ship structures. And let me say that this idea to create a testing facility for standardizing the validation of robotic inspection come from a colleague that passed away, unfortunately, but he really conceived this idea. And this idea was conceived because of this reason that I'm trying to explain now. If we think that RIT system, robotic inspection or remote inspection technologies are a measurement system, then we need to grant for this system the basic measurement theory principles that are accuracy, that are precision, that are repeatability, that are reproducibility. These are mentioned in every textbook about theory of measures. Accuracy. Accuracy means you have to demonstrate the closeness of a measurement with the true or accepted value. But then you need a true or accepted value that is a comparison term, that is the truth for you. Then the truth is hard to define on board. You cannot find the truth, at least because you don't know exactly how many defects you have on board in advance. So accuracy cannot be granted with reliable terms on board. You need precision, that is the closeness of a repeated measurements one to the other. So a measurement can be accurate but not precise, but you need to repeat a lot of measurement to obtain precision, to assess the precision. This is also difficult to carry out on board. Then you need a repeatability. So the process of measurement should produce the very same result when repeated under identical condition, meaning that the same person, the same equipment, the same method is applied. But you cannot reproduce the very identical condition on board. It's very, very difficult that you obtain an identical, completely identical condition when you measure the degradation on board. And also the reproducibility is difficult on board because you need to repeat and to produce the same result even when different people are using different equipment. So this is also difficult to obtain, even if you can. It's not impossible, but it's all quite difficult. If you are able to grant the 4 principles, then you can tell that you are validating this measurement system of degradation on board. And this is the rational scheme that we tried to implement to validate the robotic and digital inspection technology. I repeat, as a whole, a complete technology, meaning the drone, the streaming video, the pilot, everything is involved. Then let's try to be back a little bit. Which are the critical factors that may influence the performance of a survey? Then they are listed here, but what we found and where in the beginning of our research was a very interesting research carried out in the past. There was a research carried out in US that assessed the reliability of human inspection on board. So they made statistics on human inspection on board. It was very, very difficult. And the difficulty was to find the same ship, the same cargo tank, the same ballast tank inspected by more than one inspection at the same time. Almost impossible. But they did a bit of that. And they found these survey performance factors listed here. And then we tried to elaborate this result. We published a paper trying to identify which are the most important factors for human inspection and for robotic assisted inspection. And these are more or less the result we summarized in this table. I go quick. Then after that, we really started to define the protocols, the objective evaluation criteria, and to build up a testing facility to carry out validation trials of any robotic technology. I mean, a drone with a pilot with some technologies for streaming and so on. And then we decided to have testing protocol for any new technology you can imagine. How to do that? Demonstrating the equivalence between the robotic technology and the human inspection, but doing that in the framework of a testing facility and the testing protocol. So currently we have several protocols that are trying to assess several aspects of the application of the implementation of the remote inspection techniques that are ranging from piloting skill to operating skill to mobility, dexterity, to the operating time to satisfy these inspection goals, how much time you take for one thickness measurement. If the human inspector is order of magnitude faster, we don't need the robotic technology. We need the robotic technology that is equivalent. That means also efficient as a human inspector. Which kind of preparation and which kind of measurement you are going to take, thickness, of course, but also the shape of a dent, the size of a crack, and so on. And we also need to demonstrate the video streaming effectiveness, okay? So we started to develop this testing facility, and nowadays we can tell that we have a dedicated environment that is not really expected because it's already providing to some stakeholders an easy and economical way for assessing and developing digital technologies. So we have some stakeholders that are coming here to do some trials, to discuss with us, to take advantage of our previous experience. And we did testing, putting together several stakeholders, but also we realized that we need some training. People that are involved in robotic technologies are not aware of the problem of the ship, and ship inspector, ship surveyor are not aware of the reality of the technologies. We have wonderful technologies that are really ready to be used, but must be used in a proper way. So I would be very fast in telling you how we prepared the testing facility and the protocols. We went together with colleagues. These are a few of the colleagues involved in the preparation. We went in a repair yard to take parts. Then we brought the parts in our lab. And then we started assembling a testing facility that is nowadays shaped like this. And this testing facility has been improved during test session, one after the others. And this section A of the testing facility nowadays includes several parts with different conditions, structural condition, representing different ship age, representing different possibility of lightning, different representing a wide range of hull topologies, from bulk carrier to bulkheads to double bottom structure, double side structure. So we have several possibilities, and we can create different environments, sprayed water, dark or light, and so on. And we can create different protocols, I mean, different exercises, so to say, for our pilots and robots and superintendent or inspector. They need to work together. We learned that they need to work together, but it's not easy. When you have ship superintendent or ship surveyor that work together with the pilot of a drone, then they need to communicate properly. Then we have a protocol to understand whether they are able to communicate protocol. This is somehow training, but is also related to the technology. We need the technology to make the communication possible, not only when the surveyor is not on board, but even when the surveyor is on board. If you are piloting a drone, maybe it's too difficult to communicate with the surveyor. You cannot have the attention paid to the surveyor communication if you are really concentrated in piloting. So we need to create a protocol also for communication, meaning that the training and the technology should be regarded as a whole, as a unique, essential system. And then we created also section B and section C that are other parts of our testing facility where we carry out specific testing that are assessing very, very specific aspects of the technology. And we are continuously creating new protocols. One very interesting is a test that is a blind piloting test in a section of the testing facility. You have a pilot, you see in the right of the slide, in the bottom right, that the pilot is outside looking what is inside a tank, a cargo hold, and so on, but he is not aware of what is inside. Then we created several repeated structures. Such repeated structures make some confusion. They are same color, no reference point, and basically what happens is that the pilot is lost is not really able to localize the robot, to localize him or herself in the space. And that is a very important testing protocol we carried out. And it means that we need again to take into account the human factor. Generally, we have a trial arrangement that is formed by one test leader, that means one of us directing the trial. Then we have a class surveyor and the superintendent, it depends. And then we have probably a pilot or someone dealing with the robotic or digital technology involved. And then we carry out the protocols and check whether the performance is at the same level of a human surveyor. For instance, you see here a few videos of the trials, just to show you what is inside the testing facility nowadays. And these are the videos I mentioned. This is another section of the testing facility. Dirt space, dust space. They are really dangerous for robotic technologies. We had a failure of a drone because of the dust at the very beginning. Nowadays, the engine of the drone are protected much better from steel dust. Just to show another one, we had this crawler taking measurement and reconstruction with LiDAR. We had several different painted and rusted surfaces. And this is to show you that this crawler was piloted from remote. So we had the pilot of the crawler in Switzerland, and we had the inspector, the class surveyor in UK. Of course, we are in Italy. We had the ship superintendent from the ship owner in Naples. And this were the first trial carried out completely from remote. But I don't want to forget this part of our trials. All protocols have been also carried out or can be carried out by a professional surveyor that is carrying out in the testing facility the very same protocol that we are going to ask to carry out by the robotic or digital technology, by the remote inspection technology system at large. And then we have this kind of trial assessment. That means the test records that are assessed according to certain parameters that we have found. One of them, for instance, is time. The other is accessibility. And then we have different trial cards that we have associated to any type of protocol. And we are continuing to describe new protocols, because every time we have a new technology, we can try to assess the technology in our facility. And I would like to stress again the fact that we have a new a complete technology, but this technology is used by humans, and the humans need to be involved, to be considered in the validation as well. We have a team, like any survey, we have a team that is the class surveyor, the ship superintendent, and everything is together to create a judgment of the structural condition. So in the end, I would like to show these trials in the testing facility. I will be quite fast. This is the very first trial in the testing facility. You see that at the beginning, the testing facility was not fully painted, was painted only in certain parts. But then in the years, we evolved. We had we painted the surfaces because we carried out some adhesion tests of a crawler, and we realized that the coating can be ruined by the crawler, and then we need to take care of that. So the technology should not destroy the coating. And nowadays this crawler is perfectly okay. It was the robotic developer was able to improve the technology somehow, beside validating it. And we realized of several possibilities. We created some markers. For instance, now we have markers that can be moved around the testing facility, so that the many defects in the testing facility can be changed, and we can create new paths to have a blind trial. If you carry out a trial, then the same pilot is now aware of the defects. The test is not anymore the same test as before. When a surveyor boards a ship, is going to inspect something completely unknown, but then we need to reproduce the same trials, so we need to have some new thing to see, and then we cannot repeat the trials in the very same way, with the very same surveyor. So what we are doing now, training is a focus for us. Training and validation continue to be a focus. We are now engaged with autonomous technologies. This is, of course, future of research. We are discussing about coating. We are discussing about looking at the weld seam, so welding process, repairs, and so on. We are still looking at harmonization in a goal-based perspective of practical procedure training, and to speak a common language in digital technology is very important in our opinion. And the last focus that is nowadays the focus of our research, because of two national projects, is the remotization of our trials. I mean, we are trying to carry out our testing from remote, in the sense that for the time being, someone can send here a robotic technology or a drone or whatever you have in mind. And then we have now in the testing facility a set of cameras that can be deployed to see the trials from remote. And the idea is that, of course, we can test the remote inspection, meaning that someone is looking at the inspection carried out on board from remote. I'm not telling that we need to do that now, but we are looking at this possibility. But also, we would like to collect videos, and these videos could be from robot cameras, but also from our own cameras. And these videos will be used for research purposes to improve the system autonomy. So we can have the possibility to review these videos and to help in finding defect in the video. One of the difficulties is for those doing this remote inspection or doing robotic inspection is to find in a video one defect. I mean, when you have a thickness measurement, it's difficult, but then you can assess a number. But when you find a crack, when you find a dent, a distortion of a structure, that is much more difficult to assess and to compare with the judgment of a human inspector on board that is looking at with close-up survey. The result of the close-up survey, when we look at a crack or a distortion, is to a certain extent a narrative report. Then we need to jump into a digital video, and such digital video must be compared with an analogic result of a human inspector that is a narrative. So this is quite challenging today. I do believe it's still quite challenging, but artificial intelligence and machine learning seem promising techniques for doing that. So thank you very much for listening. And I close here my presentation.